Usually when we think of math, we picture this perfect, infallible machine.
Right.
Like you punch in the numbers, you turn the crank, and the absolute truth just pops out the other side. Like a flawless, perfectly polished calculator. You don't really question it because, well, 2 plus 2 is always 4.
Exactly.
Yeah.
I mean, people find a lot of comfort in viewing math as this universal constant. It feels like the ultimate bedrock of logic, right? Completely isolated from the messiness of the real world.
But then you take that flawless math and you actually hook it up to the physical world. You wire it into heavy machinery or plug it into defense systems.
Or attach it to the power grid.
Right. And suddenly that perfect machine it has a mind of its own. It starts getting confused. It starts trying to break things. And that intersection where pure math crashes into physical reality, well, that's what we're exploring today. So welcome to this custom-tailored deep dive. We are jumping into a really fascinating curriculum excerpt today titled Day 4 Inverse Trigonometric Functions Explained.
Which is quite the title.
It is. But, incredibly, it came bundled with this AI chat log detailing the actual real-world engineering disasters that happen when math goes rogue.
And we're very glad you are here with us because this material, it gets into some really high-stakes territory very quickly.
Oh, absolutely.
We're looking at the invisible safety nets that keep our automated world from just, tearing itself apart.
Yeah, so our mission for today's deep dive is to figure out how a seemingly dry, chalk dust mathematical constraint is actually the hidden force preventing industrial robots from snapping their own arms. Or like keeping digital cameras from violently spinning backward and stopping massive electrical power grids from suffering catastrophic blowouts.
It's a lot resting on some basic trigonometry.
It really is. Okay, let's unpack this because the core premise here is that math doesn't always automatically map to reality. Sometimes it needs human design boundaries just to function.
Right. And before we can understand why those massive engineering systems fail, we have to look at the foundational math. Specifically, we need to understand why the gears of that flawless mathematical machine, why they grind to a halt when you try to run it in reverse.
Run it backward, yeah.
Yeah, exactly. So the source material outlines a fundamental architectural rule for functions. To invert a function meaning, to feed it an output and have it tell you the original input, it must be what mathematicians call a bijection.
Okay, I'm going to need a translation for bijection because my high school calculus is, well, it's a little rusty.
No, fair enough. Think of it as a perfect one-to-one mapping. Every single input has one unique output, and every output connects back to one and only one unique input.
Okay.
So you can walk perfectly in both directions without ever getting lost.
Right, but standard trigonometry doesn't do that, though. Like, if I picture a standard sine wave or a cosine wave, they just go up and down. They're infinitely repeating, like ocean waves. Yeah.
Yes. And because they repeat forever, they map endless, completely distinct inputs to the exact same output height. So they completely fail the test for injectivity.
Meaning you can't trace it back.
Exactly. You cannot uniquely trace a specific height on that wave back to its original starting point.
It's like asking an automated calendar, what day does the 15th fall on?
Oh, that's a good way to put it.
Right. It's an impossible question for a computer. The 15th happens every single month, infinitely. The system would just freeze because it has 12 equally valid answers for a single year alone. You have to restrict the question to a specific month for the system to actually give you an actionable answer.
That is a brilliant way to frame it, actually. You have to actively restrict the scope.
Yeah.
And in mathematics, this solution is quite literally called domain restriction.
Domain restriction.
Right. To build an analytical inverse function, like inverse sine or inverse cosine, we cannot use the infinite ocean of waves. We have to isolate a single, continuous, non-repeating section. Basically, we put blinders on the equation.
So you basically have to just chop the wave up. Like, just pick a slice and throw the rest of infinity away.
That is exactly what the curriculum describes. It refers to this specific, mathematically agreed-upon slice as the principal value branch.
Principal value branch.
Yes. So, for example, if you take the standard sine wave, mathematicians just slice out a specific window strictly between negative pi over 2 and positive pi over 2.
Okay, let me visualize this for you. If you're looking at a graph, that window is just the bottom of the trough of the wave to the very top of the peak. Just one clean, continuous uphill sweep.
Exactly. In that primary window, the function never repeats its height. It is strictly moving in one direction. So now the mapping becomes a true bijection.
Because there's only one answer now.
Right. When you invert it to create the inverse sine function, this restricted window becomes your permanent output range. If you were to visualize this using, say, Python tools like plotting it in geometric space with NumPy and Matplotlib, the inverse transformation looks like a perfect symmetrical mirror reflection of that sliced wave across a diagonal line.
Yeah, it's visually very elegant when you see it graphed out, but it's also, it's highly artificial.
It is, and what's fascinating here is that this mathematical restriction, this artificial limitation we force onto the equation, is actually the only thing that gives the math its power to be used safely in the real world. By limiting its scope, we make its answers definitive.
And that brings us to the terrifying part of the source material.
Yeah, it gets real very fast.
Right, like what happens when engineers forget to apply those limitations? We move out of pure whiteboard theory and straight into life or death aerospace systems. Let's look at the radar scenario from the text.
Okay.
Imagine an automated anti-aircraft defense radar. It's out in the field, it's tracking an inbound drone, and its computer is rapidly trying to calculate the look angle to physically point the heavy metal radar dish at the target.
Right, and to find that angle, the radar system relies on telemetry streams, the raw X and Y coordinates of the drone in the sky. It feeds those coordinates into the inverse tangent function, taking the Y coordinate and dividing it by the X coordinate to find the angle.
Sounds simple enough, honestly. The computer divides two numbers and gets an angle.
But here's where the pure math completely betrays the physical reality. Let's play out the system fault step by step. Suppose the inbound drone is up and to the right of the radar station at coordinates 10. The computer divides Y by X. 10 divided by 10 is 1.
Okay.
The inverse tangent of 1 gives you an angle of 45 degrees.
Got it. So the motors spin the radar dish 45 degrees up and to the right. Target acquired. Everything is working.
Now suppose a different drone is creeping up from behind the radar station. It's down and to the left at coordinates -10, -10. The computer divides Y by X. -10 divided by -10 is, well, it's also 1.
Wait, really? Wait, so a raw calculator spits out a 45-degree angle for both. It physically cannot tell the difference between a target in the front right sky and a target in the back left sky.
Exactly. The pure equation is entirely blind to the difference. If the system treats the inverse tangent calculation without strict principal branch bounding to sort out which quadrant the target is actually in, it suffers a catastrophic tracking failure.
Wow.
The unconstrained division just compresses two entirely different physical locations into the exact same ratio.
So if that second drone is creeping up from behind, the defense system computes the math flawlessly, gets 45 degrees, and points the radar dish 180 degrees away from the threat, literally staring at empty sky.
Yes. The fire control system is rendered completely useless, despite doing the math perfectly. The math was right, but the application to physical reality was fatally flawed.
That radar problem is, it's terrifying because it highlights a massive software blind spot. But what happens when that unbound math crashes into solid steel?
That's where things get physical.
Right. The source notes dive into how this exact same principle, the principal value branch, is used as a physical safety constraint in other massive industries. Let's talk about moving metal. Let's talk about robotics.
Okay, yeah. When you look at an articulated robotic arm on a factory floor assembling cars, it's a marvel of automation. But the controller running that arm, it doesn't think in terms of an X and Y grid.
Right. If you want the robot to pick up a car door, you can't just tell the motors, go to coordinate X5, Y10. Motors don't understand coordinates. They only understand rotation and angles.
Exactly. So the system bridges that gap using a mathematical process called inverse kinematics.
Inverse kinematics.
Right. When you give the robot a target coordinate, the computer draws an imaginary triangle between the robot's shoulder joint, its elbow joint, and the target object. It uses the law of cosines to calculate the exact angles those joints need to bend to reach the item.
Okay, I follow.
And to isolate the specific angle for the elbow joint, the system runs the physical lengths of the arm segments through the inverse cosine function.
And here's where it gets really interesting, because we are back to domain restrictions. The mathematical constraint for the inverse cosine function is incredibly strict, right? Its input domain is only between -1 and +1.
Yes, exactly.
It physically cannot accept a number outside of that tiny window. So what happens if the computer draws that imaginary triangle, crunches the lengths of the robotic arm, and tries to feed the inverse cosine function a number like, say, 1.05?
The math engine spits out an undefined error.
Wow.
But this isn't just a software glitch. In physical reality, an input greater than 1 means the imaginary triangle the computer drew is physically impossible to close. The math is acting as a hard boundary for physical space, triggering what engineers call a workspace violation.
Workspace violation. So the math is literally screaming, the object you want me to pick up is physically out of my mechanical reach.
Right.
The metal arm cannot stretch that far without ripping itself off its base. The equation breaks exactly where the physical world ends. That is wild.
It is. And it goes even deeper into physical safety. Let's look at the output range of that inverse cosine function. The principal value branch restricts the output strictly to between 0 and pi radians.
Which translates to 0 to 180 degrees?
Right. Because of this mathematical limitation, the inverse function naturally refuses to output a negative angle.
So what does that mean for the steel arm, like practically?
It means the math safely and consistently forces the robotic arm into an elbow-up structural position. If you think about a robot operating on a crowded factory floor, you generally want its joints pointing up and away from the machinery and the human workers below it.
Oh, it forces a default safety posture.
Exactly.
Because if you want the robot to reach that same exact coordinate but in an elbow-down posture to, say, sneak under an obstacle, the mechanical controller can't just rely on the raw inverse cosine function. The math just won't let it.
No, it won't. The programmer has to explicitly map the negative mirror image of that angle to override the math. The principal branch acts as a physical guardrail.
It's incredible how abstract trigonometry naturally dictates the safe behavior of industrial metal. But let's pivot from solid steel to something much harder to visualize: invisible electricity.
Okay, jumping into the grid.
Yeah, because these same mathematical guardrails are literally keeping the power grid from melting down.
This brings us to heavy industrial power systems, alternating current phasor analysis, and power factor correction. In massive electrical grids, electrical impedance behaves like a 2D vector.
Okay, wait, slow down. Impedance. Vectors. I know what a massive factory motor is, but the source text talks about inductive loads and capacitive components causing current to lag. Give me an analogy here, because it sounds like you're talking about pushing a heavy cart where the wheels haven't caught up to your hands yet.
Sure, yeah. A tandem bicycle is actually a great way to visualize it.
Okay, a tandem bike.
Think of the voltage as the person pedaling up front and the current as the person pedaling in the back. In a perfect, highly efficient power grid, they pedal in perfect sync. They hit the top of the pedal stroke at the exact same millisecond.
Okay, so they are riding the wave together.
Right. But the real world is messy. When you plug in massive inductive loads, like giant electric motors spinning up in factories to crush metal, it resists changes in current. So going back to our bicycle, it's like the person in the back suddenly gets sluggish. They are still pedaling at the same speed, but their stroke is delayed. The current is lagging behind the voltage. They are out of phase.
And the measurement of how wildly out of sync those two riders are is called the phase angle, which, according to the source material, is calculated using our old friend, the inverse tangent function.
The very same function from the drone radar problem earlier. But in the power grid, the principal branch is doing crucial diagnostic work.
Right.
The principal branch of inverse tangent isolates the grid state perfectly between negative 90 degrees and positive 90 degrees.
Right.
If the output angle is greater than 0, the grid has a net inductive load. The front rider is pulling away from the back rider.
Because of all those heavy factory motors. And if the angle is less than 0, the load is capacitive. The current is actually leading the voltage.
Exactly.
But the stakes here are massive for anyone listening who enjoys having their lights turn on. If the voltage and current get too far out of sync, the power grid becomes wildly inefficient. You are generating massive amounts of electricity at the power plant that just isn't doing any actual work.
Yeah, it's just violently heating up the transmission wires, threatening to melt down the infrastructure.
Which raises a really important question. How do utility companies prevent an entire city grid from overheating and blacking out?
Yeah, well, they have to maintain a power factor as close to 1 as possible, meaning the angle between the riders on the bike is brought back to 0. And they achieve this dynamically using heavy industrial microcontrollers.
And those microcontrollers are running this exact restricted inverse function we've been talking about all day.
They are continuously monitoring the output of that inverse tangent calculation. The restricted principal branch gives them a definitive, unambiguous angle. It tells the system exactly how out of sync the grid is at any given millisecond.
Okay.
And then the microcontroller uses that exact angle to calculate the precise amount of microfarads of capacitance to dynamically inject back into the grid from giant capacitor banks.
Oh, wow. So it acts like a counterweight.
Yes, exactly.
They are constantly balancing this invisible seesaw of electricity using a bounded trigonometry function. If that function wasn't restricted, like if it gave multiple or ambiguous answers like the radar did, the grid controller wouldn't know whether to add capacitance or remove it.
Right, it would be guessing.
It might dump more energy into an already overloaded system, and the whole city cascades into a blackout.
So the domain restriction provides a single, actionable truth inside a wildly chaotic electrical system.
That is just amazing. So we've solved physical space with robotics, and we've solved invisible energy with the electrical grid. But what about purely digital environments?
Oh, this is a fun one.
Because a video game or navigation algorithm doesn't have physical bounds to hit, and it doesn't have electrical wires to melt. How do software engineers solve the radar ambiguity problem we discussed earlier?
This is where we see computer scientists explicitly engineering mechanical hacks to get around the mathematical blind spots.
Yeah.
We're looking at 3D graphics engines and autonomous drone navigation code.
Set the scene for us. We've got a 3D game engine. There is a digital camera that needs to smoothly track a moving asset like a race car across the X and Y plane.
Right. To calculate the horizontal viewing direction, which is often called the yaw angle, the graphics pipeline tracks the change in the car's Y coordinate and divides it by the change in the X coordinate. It then maps that ratio through the standard inverse tangent function to find the angle the camera should point.
Which brings back the quadrant trap.
Yes.
The standard inverse tangent function only outputs in quadrants 1 and 4. Visually, it only covers the right half of the circle.
Let's connect this directly back to the defense radar failure. It's the exact same geometric trap, but happening inside a virtual world. Say your video game race car moves into quadrant 2. It moves backwards on the x-axis and forwards on the y-axis. We'll say a change in y of 5 and a change in x of -5.
Okay, 5 divided by -5 is -1.
Now imagine the car moved into quadrant 4, down and to the right. Y is -5, and x is +5. -5 divided by +5 is also -1.
Right, the direct division just destroys the raw coordinate data. It compresses two completely opposite directions on the map into the exact same ratio.
Exactly. The standard math function takes that -1 and confidently returns -45 degrees, which means if your race car drifts into quadrant 2, the top left of the map, your digital camera violently whips around and points completely backward, staring away from the action.
It's the drone radar failure all over again.
Yep.
If you're listening to this and wondering why your video game camera doesn't constantly break every time you turn left, it's because of a fascinating software workaround. So what does this all mean? How do programmers fix a hole that exists in the pure math itself?
Well, they abandoned the standard mathematical notation entirely. Software engineers introduced an extended computational variant called ATAN2, that's ATAN2. The SU stands for two arguments.
Yeah.
Instead of taking a pre-divided ratio, it takes the two distinct coordinates, y and x, separately.
Oh, so it preserves the fact that x is negative and y is positive before any math even happens. It keeps the context.
Yes, context is everything here. ATAN2 uses programmatic conditional branching. It's essentially a series of if-else statements built as a shell around the original restricted math functions.
Okay, so ATAN2 takes the raw coordinates. But how does the software actually use them to fix the blind spot? Is it just running a bunch of if-then scenarios behind the scenes to physically expand the map?
It acts as an algorithmic traffic cop.
A traffic cop.
Yeah. If the x-coordinate is positive, ATAN2 just runs the normal inverse tangent function. Everything is fine. But if the software sees that x is negative and y is positive, meaning we are in quadrant 2, it runs the normal math and then artificially adds pi, or 180 degrees, to the final result.
Okay, making up the difference.
Right. And if x is negative and y is negative, meaning quadrant 3, it runs the math and subtracts pi.
It's quite literally duct taping a manual override onto a pure math equation.
It really is.
It's like the engineers looked at the flawless mathematical machine, saw that it couldn't turn left without crashing, and just bolted a mechanical lever onto the side to manually spin the output 180 degrees whenever they needed it to see the whole map.
And this programmatic branch expansion seamlessly shifts the functional mapping across a full 360 degrees. It avoids the software blind spots entirely without violating the foundational mathematical rules. It forces the system to acknowledge the entire reality of the map.
We've covered an incredible amount of ground today. Let's bring it all together for you. We started with a purely abstract, theoretical concept, the idea of bijections and domain restrictions, just, slicing up an infinite wave on a chalkboard so we could run an equation backward without breaking the calculator.
Yet we've seen how that purely abstract rule serves as the load-bearing pillar for physical engineering.
It's the foundational logic that keeps robotic arms operating within their mechanical limits, preventing an industrial machine from trying to stretch into a dimension it physically cannot reach.
Right.
It's the diagnostic tool that balances the invisible seesaw of our electrical grids, preventing massive heat cascades and blackouts. And it's the hurdle that software engineers had to explicitly code around with the arctan function just to stop digital cameras and autonomous drones from flying backward.
If we connect this to the bigger picture, the lesson from the source material is profound. Math isn't simply about finding the right answer. In engineering, math is about actively restricting the infinite possibilities so that the answer you get is actually useful and physically safe in the real world.
It is about putting human-designed guardrails on infinity. And it leaves you with a final thought to ponder as we wrap up today's deep dive. If all of our physical engineering, our heavy machinery, our defense systems, our power grids, if all these vital automated systems rely on these very specific human-defined principal branches to safely navigate reality effects, what other blind spots might exist in the raw, unconstrained algorithms that are increasingly running our world today? Because, as we've seen, the math machine itself might be flawless, but until we tell it exactly where the edges of reality are, it just might turn around and point the radar in the exact wrong direction.